again to my classes on fundamentals of electrical engineering. We were on electrical machines. We finished DC machines in 2 sections, or rather 4 sessions, 8 and then we moved on to transformers. Transformers, because of the questions that are repeated, there are only 2 sections. In the earlier section, we had 3 sessions, and this section also we have 3 sessions. Okay, so in this session we talk mostly about autotransformers. In fact, a major chunk of problems that come in gate examinations happen to come in the autotransformer domain. Moreover, autotransformer is a very useful kind of equipment which gives rise to quite a lot of savings, not just in energy but also in terms of copper. Okay, so let's try to understand how we can easily solve problems in autotransformers. Okay, so let's move to the first question. I suppose, this is a little different, but as I said earlier, they are not just autotransformers that are there in this session. There are other questions also. Okay, and these kinds of problems, the first problem that you are going to do soon enough, has a circuitry kind of way of finding a solution, but I have consolidated it all together in a single expression, the meaning of which I'll give to you, such that you can remember it and do it directly, okay, rather than writing out the entire circuit and solving it in a very detailed manner. Okay, so let's move to the question. The self-inductance of the primary winding of a single phase 50 Hertz transformer. So it's only for a transformer that this derived value is true. Okay, it's 800 millihenry. So L1 we have 800 millihenry, and that of the secondary winding is 600 millihenry. So on the secondary we again have a inductance, and it has, so we call this L2 as equal to 600 millihenry. Okay, the mutual inductance. Okay, so this is the difference between the rest, because there is no conductive connection, there is only inductive coupling between the two. Okay, so we can't use some of the other expressions. We have to use the special equation, or you have to write it all together. You have to write it all as in terms of equations of 2 loops, and then got to do it. Rather than that, I suppose you can use this expression that I have put on the slide. Okay, the mutual inductance between these 2 windings is 480 millihenry. The secondary winding of this transformer is short circuited, and the primary winding is connected to 50 Hertz single phase sinusoidal voltage source. The current flowing in both the winding is less than the respective rated current. Otherwise, there could be saturation, and all these things would not be true. Okay, the resistance of both windings can be neglected. Okay, in this connection, what is the effective inductance in millihenry seen by the source or seen from the primary side? Okay, the best way to understand is in this manner. That is, because of the dot terminal not receiving the current in both on both sides, there will definitely be a minus sign. Okay, so that's one thing. So we'll have L1 minus m square, because always this is going to be this is a kind of a coupling. So we'll have m square divided by L2. Rather, there's another way of expressing the whole thing. If you write it out in equations, it is the same as equal to L1 L2 minus m square by L2. So that's all that's done in this. So we have L1 as 800, L2 as 600. So L as 800 into 600 minus 480 square divided by L2, which is equal to 600. Or L1, that is 800, minus 480 square, that is m square, divided by 600. Okay, so that also yields a value equal to 416 millihenry, because everything is in millihenry. Okay, so that's an easy way of doing it. The rest, okay, in most of these problems you'll see that, okay, again this is also a similar kind of problem, but it's a little different. Okay, again, what we understand out of coupling, what we understand by how much of contribution is there through the mutual inductance, all these come handy. Okay, so let's read the second problem. The parameters measured for a 220 volt, 110 volt, 50 Hertz single phase transformers are self-inductance of the primary winding, just as we saw earlier, 45 millihenry. Then self-inductance of secondary winding, 30 millihenry. Mutual inductance between primary and secondary winding is equal to 20 millihenry. Okay, so all 3 are given. Okay, using the above parameters, the leakage. Okay, so L1, as we saw earlier, L1. Okay, so L11, and then L1. Okay, leakage is LL. LL1, LL2, and magnetizing inductance LM. Okay, inductance as referred to primary. Okay, as we said, what is seen by the source. Okay, in the equivalent circuit respectively are. Okay, so we don't, okay, as I said earlier, there are sets of equations that we write for the circuitry, and here the circuitry is directly being used. Okay, what is going to come in the circuitry? Okay, so what will come on the primary with respect to the first, that is what will the primary see as L1? Okay, it will see the same as, what will it see as L1? It will see the same as equal to L1 minus 2m. Okay, so because as I said earlier, there is the negative comes because of this, and then m occurs twice. That's the reason why we have to deduct 1. So we have L1 minus 2m. Okay, so we have L1 minus 2m means 45 into 2 minus 20. Sorry, L1 is 45 minus 20 into 2. So we get it as equal to 5. Okay, so there are two answers with 5. That also tells us that one of them must be true. Okay, so we can say that A or B is true. Then we move on to how the secondary can be, that is the inductance on secondary side L2, how it can be projected onto the primary side. So we use the turns ratio 220 by 110, that's equal to 2 square that. Okay, so 2 square into L2, that will bring it on the primary side, then minus 2. Okay, so we have 2 times k square is 4 into 30 is 120, 120 minus 2 into 20, that gives us another 80 millihenry. So obviously the answer B is right, but at the same time we'll just mention about the third quantity where we see that it is going to be 2m. Okay, so because as I said earlier, it's always going to account it twice. Okay, and the reason is also given there because we see that mutual inductance can be seen as V1 causing I2. So V1 by I2 will give you some understanding of mutual inductance, and then it has to be multiplied because it's neither on the primary nor on the secondary. We multiply by V2 by V1. Okay, so it's just a concept-wise way of doing the problem. Okay, let's hope that you are able to absorb it, or you are able to accept it. Okay, so that's it. So let's move to the third problem. Okay. What is it? We are having 3 windings, okay, and the windings at the one side is energized by a 400 volt 50 hertz source, and we seem to be having a voltmeter measuring perhaps the voltage, because it's voltmeter. All okay, the voltages are collected from all the windings. Okay, so right from the third winding, next to the mid winding, and then the first winding. Okay, and the ratios are given for the transformer. So it could also be the voltage, because 400 is to 200 is to 200 is given, and there are dots as well. Okay, in the earlier two cases, the first two have dots, okay, on the upper terminal, but the third winding has the dot on the lower terminal. Okay, so obviously what is the voltmeter could be the question. Okay, so let's read 400 by 200 by 200. Okay, as is written here, volt 50 hertz 3 winding transformer is connected as shown in the figure. The reading of the voltmeter will be what? Okay, so so we have 200 volts here. So let's start picking up the voltage from the point of view of the voltmeter. What we have there? We have, okay, so let's put a positive sign for all the dotted terminals. Okay, because that's how it happens. That is, we have 400 volts across the first winding, which is connected directly to a source. So it induces a voltage in the second winding. Okay, it also induces a voltage in the third winding, such that the dotted terminals are positive in all 3 cases. Okay, so we see that we are having a potential rise in the first winding where the voltmeter starts picking up. Okay, that's equal to 200 volt. Then we see that we are having another potential rise, okay, because it has reached the bottom terminal, and then it goes from an undotted to a dotted terminal, or a minus to a positive polarity in the second winding, and then it comes to the junction between the two coils, and then there is a potential drop. Okay, and how much is it? 400 volt. Okay, 200 plus 200 minus 400. Okay, so this just gives us an understanding about 2 or 3 things. One is, of course, what do you mark as polarity, a positive polarity. Okay, of course the dotted terminal is better marked as polarity, and when you are given a voltage, when you're giving a voltage to particular winding, every winding which has a dotted terminal, it has the same polarity. Okay, so that is if they are induced from with respect to each other. Okay, so that's the way that you have to go. And then what does the voltmeter pick up? It picks up all the voltages, so you can go from one end to the other end of the terminals of the, or one terminal to the other terminal of the voltmeter, and pick up voltage. Okay, so you pick up 2 rises and 1 drops, and the rises happen to be only 200 volt, but the drop happens to be a 400 volt, so the voltage is equal to 0. Okay, so that's it, and we go to the Next one, there is the fourth problem. What does it say? It's all English now. A single phase 2 kVA 100 by 200 volt transformer is reconnected as an auto transformer. Okay, so this is interesting. We have started the auto transformer, okay, such that its kVA rating is maximum. This is the reason why we reconnect single phase transformers to give us an auto transformer. Okay? In fact, most of the laboratories use auto transformers such that any kind of voltage can be manipulated. The new rating in kVA is what? Okay, so how do you do this? All the problems in the same manner. Okay, so true kVA tells us about a current rating for each of these windings. Okay, and then all these the windings can be put together. That is 200 and 100 volt can be mounted one on top of the other physically too, and electrically as well. So we can get what is called as 300 volt, okay, in total, because one can stand 200 volt, the other can stand 100 volts, so 200 plus 100, 300. Okay, but what about the current? Okay, so now we can see what gives you the maximum current. Okay, so 2 kVA divided by 100 gives us 2 kVA, that is 2000 divided by 100 gives us 20 amps. Okay, so 20 amps multiplied by 300 volts will give you 6 kVA. Though the transformer was earlier rated only for 2 kVA, just by connecting together windings, okay, and loading it to its maximum level, we see that we are having a 6 kVA transformer emerging from a 2 kVA transformer. Okay, so this is why the transformers save space, save material, as also save quite a lot of efforts. Okay, so let's move to the fifth problem, another auto transformer. So now we are ready with the auto transformer. What do we have there? The dotted terminals are shown, which shows that they are mounted one above the other. And so we see that 1000 plus 100 volt is equal to 1100 volt as guessed. Okay, and then we need to find out the current. Okay, so how do you do that? Take the kVA ratings, divide it by the smaller voltage rating, so you will get the largest current that's possible. Okay, so multiply the possible voltage by the possible current, it will give you the kVA. So what do we have there? 50 kVA, a single phase 50 kVA, 1000 volt by 100 volt. Okay, so the 50 kVA, 1000 volt by 100 volt, we saw that 1000 and 100 were put one above the other. We had a construct of 1100 volts, and then 50 kVA divided by 100 volt will give you 500 amps. Okay, and that 500 amps, okay, multiplied by 1100 kVA will give you 550 kVA. Okay, so from a 50 kVA you magnify it to a 550 kVA. Okay, so that's the utility of an auto transformer. Okay, okay, more auto transformers are in the making. Sixth problem. A single phase 22 kVA, 2200 volt, 220 volt, 50 hertz distribution transformer is to be connected as an auto transformer to get an output voltage of 2420. How is it possible? We have 2200 volt winding on one side. Over and above that, add 2220 volts. So what do you have? 2420 volt. Okay, so it's possible. Okay, so much of voltage can be catered to by this kind of transformer, which has been converted from a single phase to an auto transformer. Okay, its maximum kVA rating as an auto transformer is okay, very simple. 2420 multiplied by the maximum possible current. So how do you get that? 22 kVA divided by the smaller voltage, which is 220 volts. So 22 into 1000 divided by 220 will give you, yeah, so you can multiply them all together at one go, and you can see that it's the same as equal to 242 kVA or 242,000 VA. Okay, so the seventh problem also should be the same. Okay, these kinds of problems recurred. That's the reason why this session can go very quickly. Okay, 200 volt, 400 by 400 volt, 50 hertz, two winding transformer is rated at 20 kVA. Immediately we see that the possibilities of a 600 volt auto transformer. Okay, that is at the output you can have 600 volt. You can give either a 200 volt input or a 400 volt input, but the output can be 400 plus 200, 600. Okay, and the current can be that there's a maximum kVA rating which is 20 kVA, which is limiting the current in the higher winding. So the lower winding you can definitely find out. That's the reason why 20 kVA divided by 200 volt. 200 volt is giving us a big ampere. Okay, and that ampere multiplied by 600 is going to give us the maximum possible kVA. Okay, so let's move on. Its windings are connected as an auto transformer of rating 200 by 600. Okay, so 200 is the input side, 600 is the output side. Okay, it could be 400 as well. Okay, resistive load of 12 ohms is connected to the high voltage 600 volt side of the auto transformer. The value of equivalent load resistance as seen from the low voltage side is what? Okay, So now we have what is called as, we need to find out K. Okay, before that let's try to find out the current. Okay, so we have 20 kVA divided multiplied by 1000, okay, divided by 200, telling us 100 amps. Okay, now what do we have? We need to find out what is called as K. Okay, so what is K? We have, it's already given 200 by 600, because 200 is primary, 600 is secondary. So 200 by 600. Okay, so now we see that we can have what is called as, we have 12 ohms. Okay, and 12 ohms, it can be multiplied by, when it has to be taken to the primary side, it has to be multiplied by K square, or 1 by 9. So 12 by 9. So it's as simple as 1.33. The current was not required. You need not calculate it. Okay. Yeah, and more auto transformers as can be seen here, N1 and N2. There's a V output, and we give as input only 3300 volt. Okay, we get a larger output. How much do we get? The 50 kVA, 3300 by 230. Okay, so 3300 is the input. Over and above, add to it 230. So we have 3530 volt as the output. Okay, possibility. Okay, single phase transformer is connected as an auto transformer shown in figure. Okay, the normal rating of the auto transformer will be. So it's okay, we have 50 kVA divided by 230 volt. Okay, 50 into 1000 divided by 230 multiplied by the total possibility of the voltage 3300 plus 230, that is that gives us 3530. So when you multiply it together, you see that. Okay, we can even go for rough calculations because the answers are separated in a very drastically different manner. So we can see that the last answer, that is 760. The only nearness is between C and D, but D is going to be the correct answer. Okay, so without much of multiplication, just by cancelling a few things, you can find the answer. Okay, so of course that's left your will and pleasure. Okay. Okay, more auto transformers or what? Let's see the figure. Okay, this is the ninth problem. The figure above. Okay, what is the figure? We have two coils A, B, C, D. Coil 1, coil 2. Both have the dotted terminal on the upper terminal. Okay, and what is given is the figure above shows coil 1 and 2 with dot markings as shown, having 4000 and 6000 turns respectively. But the coils have a rated current of 25 amps. Okay, so they can carry only 25 amps. Coil is excited with single phase 400 volt 50 hertz. This time we have given the current. Okay, is excited with single phase 400 volt. Okay, so we have, the turns are okay, but we give only 400 volt. Okay, so if you give 400 volt on this side, 4000 by 6000 tells us that you can get 600 volt on the other side. That's on coil 2 side. Okay, but what is the question? The coils are to be connected to obtain a single phase auto transformer. Okay, and what is that? You give 400 and you get 400. You get 400 plus 600. Okay, that's okay, and that's what you get. Okay, together to give you a bigger output of 1000 volts. Okay, so 400 by 1000 volt auto transformer to drive a load of 10 kVA. Now we have to drive a load of 10 kVA. Okay? Which of the options given should be exercised to realize the required auto transformer? Okay? So obviously, to get an auto transformer, you have to, okay, so how do you connect them? Okay, this is the question. So as I said earlier, one has to be atop the other. Okay, so what do you do? A and D. Okay, because coil 1 creates a voltage which is positive at the positive terminal at a point of time. Okay, so it should be true on for both the coils. Only then they can get added together. So we have A and D can be shorted, and B can be the common reference, and C can be the output terminal. Okay, so let's see what we have such a situation. Yes, connect A and D together, and then let B be common. Okay, so option number A immediately tells us that A and D need to be connected together. That's the only possibility. B will be at the base, so it's called as the reference or the common, and then C can be the output terminal. So this is it. Okay, in the auto transformer obtained in question 30, this is called as question 30. The current in each coil is what? Okay, so I just put a figure there. That is, we are having C, B as reference or as common. A and D have been connected together. Okay, and rated current is equal to 25. Okay, so we see that we require 10 kVA, and 10 kVA has to be delivered at it has to be delivered. The coils have to be connected to obtain a single phase. Okay, and the auto transformer to drive a load of 10 kVA. Okay, so 10 kVA divided by 1000 volts. Okay, that tells us that it's going to be it's going to be 10 amps. Okay, so 10 amps will be 10 kVA divided by 1000 volts, because so the top coil will have 10 amps. Okay, and then what is going to happen is that since the coil can be rated as 25 amps will go to the load if required at point. Okay, and then the remaining. Okay, so Kirchhoff's law. Okay, 10 here, 25 on the other side, so 15 is going to, okay, or 10 and 15 are going to come together to cater to 25 amps for the load. Okay, yeah, for the mid point. Okay, that's all. Okay, so let's see. Yeah, let's see the 10th problem. A single phase 50 kVA 250 by 500 volt two winding transformer has an efficiency of 95% of full load. Okay, so we are going back to efficiency. Unity power factor. It is reconfigured. Okay, so it is still an auto transformer problem, but the efficiency is given as 95% as full load. Okay, unity power factor. So this is unity power factor 95%. Okay, and it has, yeah, and it is reconfigured as a 500 volt 750 volt. Okay, so we have, yeah, 500 and 250 together, 750 volt. Okay, auto transformer, its efficiency at its new rated load at unity power factor. So unity power factor is the same and its new rated load. Okay, so let's see, the new rated load could have changed. Okay, so let's start with the total loss at efficiency. Okay, so we start from the very beginning. We see that efficiency is equal to 0.95. Okay, so we have a 50 kVA, yeah, 50 kVA, it is a 50 kVA transformer. So 50 kVA divided by 0.95. Okay, so since it's kVA and unity power factor, as is mentioned before, as also as also full load. So 50 divided by, so 50 kVA has now become kilowatt. Okay, because multiplication by two ones. One is for the unity power factor and other is for the for the full load. Okay, so we have 50 divided by, so that 50 kilowatt divided by 0.95 gives us the input. Okay, divided by subtract 50 from it, because that's the output, you get 2.63 as the kilowatt. Okay, so this is the first step. Okay, now we move on to the next step. What do we have? We need to find out what is the new output. So how do you find out new output? It's the possibility, the total voltage that is possible, which is equal to 750 volt multiplied by the total the new current. Okay, so 50 kVA again divided by the smaller winding, which is equal to 50 kVA. So 50 into 1000 divided by 250. Okay, multiplied by 750, which is going to be the total voltage. Okay, I suppose this is clear. Current we had already calculated. The same way we are calculating again. 50 into 1000 divided by 250, the smaller winding, and that multiplied by the highest voltage possible, which is 750. So this is the new capability of the machine, which is equal to 150 kVA. It is kilowatt. Okay, at full load at unity power factor. Okay, so earlier it was 50 kilowatt, now it is 150 kilowatt. Okay, and now we are having 150 output divided by 150 plus the loss 2.60. That doesn't change because everything, the copper loss and the iron loss happen to be the same. Okay, so that gives us an efficiency of very huge efficiency. This is the market difference that we have when we use the auto transformer. The efficiency increases from 95% to 98.27. I suppose this is clear. Okay, so last problem. Okay, in this session, a 400 volt and by 100 volt 10 kVA two winding transformer is reconnected as an auto transformer across a suitable voltage source. The maximum rating of such an arrangement should be. Okay, so far we've been doing the same thing. Okay, we had what is called as 10 kVA, so that divided by 100 volt will give you the current. Okay, and 400 plus 100 will give you the total voltage possible, which has been done, and that gives us 50 kVA. So that's going to be the rate, the new rating. Earlier it was only 10 kVA, now it has jumped by a factor of 5. So we are having 50 kVA. Okay, I suppose mostly we did auto transformer problems. Okay, even efficiency is improved is what we saw. The load delivering capacity increases dramatically. The voltages add together. The voltage capabilities, okay, I would say, add together. The current capability also increases because the same current capability is used for both the windings because of the benefit that the entire 10 kVA will have to be will drive a larger current through the smaller winding. So we take that as the rating, and then so we see that a larger capability builds up for the auto transformer. Okay, so this is what we have seen in this session. I hope it has that you, if any problem comes in this area, you'll be able to do it very nicely. Okay, thank you.